Hello, my name is Rola Wael. I'm a 5th year student at Princess Sumaya University for Technology. This video is for the microwave engineering class, which is supervised by Professor Abdallah Al-Zoubi. So, I'm going to solve an example for stability and constant gain circles on Smith chart using the Ketab Studio software and Matlab calculator. So this is the example I'm going to solve. Plot the 210 minus 1 dB input and output constant gain circles for a gas MOSFET with the following S parameters. S11 equals 0.707 with a phase minus 155 degrees. S12 equals 0. S21 equals 5 with a phase 180. S22 equals 0.51 with a phase minus 20 degrees. The second part of the example is to find the load impedance for maximum power gain and source impedance for maximum output power. So, step 1 is to use the Matlab calculator to enter the S parameters and then check for the delta and K parameters for stability conditions. So this is the Matlab calculator and these are the S parameters of the example as shown here. Now, to check for stability, first we go to the basic data button and find the delta. It's obvious that delta magnitude is 0.4, which is less than 1, and this satisfies the stability condition. Second, we find the K parameter, and it is infinity, which means that the system is unconditionally stable. Now, we go to the stability circles. We don't need this plot. Okay, stability circles. The radius for the source and the load stability circles are 0. So this means that there is no stability circles for this system and it is unconditionally stable. Okay. Now, to start drawing the constant gain circles, we first draw a line from the origin to S11 conjugate, and for the output constant gain circles, draw a line from the origin to S22 conjugate. Second step is to find the input constant gain circles, maximum source gain from this equation, which is 1 over 1 minus S11 squared magnitude, which numerically equals 2, and in the dB scale it equals 3. This means that the 2, 1, 0 and minus 1 dB gains are less than 3 and are available. So we are going to plot them. But for the output constant gain circles, the maximum load gain from this equation, 1 over 1 minus S22 squared magnitude, equals numerically 1.35 and in the dB scale 1.3 dB. This means that the 1, 0, minus 1 are less than 1.3 and are only available, but the 2 is larger than 1.3, which means that we cannot draw a constant gain circle for the 2 dB gain. Now we go to the Matlab calculator and click on the constant gain circles button and put let's start with 2. Click on the constant gain circles. So from here we can find that this is the radius and this is the magnitude, but these values are in the reflection coefficient scale, so I summarized them but in the centimeters scale to ease drawings and calculations. So from here, as you see, we can put all the dB gains and find the radius and magnitude, and same for the load. So it's important to note here that as we said before, we can draw the constant gain circle for the 2 dB gain. So even if we put it in the Matlab calculator, check what we see. Radius equals 0. So this means that we can't draw the constant gain circle for the 2 dB gain, and it does not exist. Okay. So this is the tables I summarized in centimeter scale for the magnitude and the radius. Now to start, this is the Ketab Studio software. First of all, we're going to import the Smith chart PDF file. And as we said, starting from the origin to S11 conjugate, which is the 155 degrees. Okay, so the phase is here. 2, 4, this is 155 point. Now I'm going to use the ruler to draw the line. And I must be very specific. Okay. I'll use the pen. So this is the line from the origin to S11 conjugate. I don't need the ruler. First we locate the 3 dB point, which is the maximum source gain, and its magnitude is 0.707, and as we said, it is in the reflection coefficient scale. So we take the compass to the reflection coefficient scale and determine the 0.707 point, which is approximately here, and back to our line, starting from the origin, determine the 3 dB point. So this is the 3 dB point. Okay. Now we'll start drawing the constant gain circles. I have this summarized table. For the 2 dB gain at source, of course, the magnitude is 5.06. So use the compass and starting from the origin, this is the 5.1. Draw the point, and from this point we'll draw the circle. The circle has a radius of 2.05, which is approximately 2.1. So 2.1, and draw the circle. So this is the 2 dB gain. Okay. Now for the 1 dB gain, the magnitude is 4.4. So back to the origin. And this is 4.4. Determine the center, go to the center and open the compass with a radius that equals 3. So this is 3. Draw the circle, and this is the 1 dB gain. Okay, now for the 0 dB gain at the source, its magnitude or the center is at the 3.8. So from the center, 3.8. Determine the center, and from this center, the radius is 3.8 also. Sorry, So this is the 0 dB gain circle. Notice that the 0 dB gain circle passes by the origin, and this means that it has no reflection. Now for the -1 dB, its center is at 3.25, so back to the origin and 3.2. So the center is here, and from this center we're going to draw a circle which has a radius of 4.5. So 4.5 is this. This is the last circle for the constant gain circles at the source. -1 dB. So again, just to make sure, constant gain circles are the input. Okay. Now repeat the same steps but for the output constant gain circles. First, draw the line. So we start from the S22 conjugate point, which is at the 20 degrees phase, and it's here. Okay, so we draw the line using the ruler from the origin to the 20 degrees. Okay, and this is the line. We don't need the ruler. Now, to determine the 1.3 dB point, which is the maximum gain at the load, go to the reflection coefficient scale to determine the 0.51. 0.51, which is approximately here. Now back to the line. Oops. Okay. Now we need the pencil. This is the 1.3 dB. Okay. Now back to our table. Of course, as we said, we can draw the constant gain circles for the 2 dB gain. We start from the 1 dB, which is at the center of 3.9 centimeters. So from the origin, this is 3.9. So its center is here. And its radius is 1.59, which is approximately 1.6. So 1.6 centimeters. And this is the 1 dB gain. Okay, for the 0 dB gain, its center is at 3.28 and its radius is the same. So from the origin, 3.38, which is approximately 3.4, 3.28, which is approximately 3.3. So this the center is here, and the radius is the same, 3.3 centimeters. Oops. Okay. And again, it's correct because it passes through the origin. 0 dB gain. Now for the last one, which is the minus 1 dB, the center is at 2.7. So back to the origin, and 2.7. This is the center. Okay, its radius is 4.3. 4.3, and draw the circle. So this is the last circle, which is the minus 1 dB. Okay, and these are the constant gain circles and the output. Note that from these circles, as long as the gain is larger, the circles are smaller, and vice versa. As in here, this is the 2 dB gain at the source, and it's the smallest circle, but the minus 1 dB has the largest circle. Okay, now for the last step, to find the source impedance for maximum output power, start from the maximum source gain, which is the 3 dB point, and move on constant resistive or conductive circles or both to reach the origin or matching. To find the load impedance for maximum power gain, also start from the maximum load gain, the 1.3 dB point, and move on constant resistive or conductive circles or both to reach the origin. Okay, on the Smith chart, this is the 3 dB point, which is the maximum source gain. We first read its value and call it ZA. So ZA equals 0.18 plus J 0.21. So from this point, we're going to move on either a constant resistive circle or a constant conductive circle to reach the origin. So these are the constant conductive and constant resistive circles for the origin. I'm going to mark the constant conductive circle for the origin to find the intersection point with the 3 dB point. And moving from the 3 dB point, we can see that this is the intersection point. I'm going to mark it. and then read its value. So I'll call it Zi. So Zi equals 0.18 plus J 0.38, and for the admittance Yi equals 1 minus 0.23. Yes, 0.23. And of course the Z0 and Y0 equals 1. Now moving from the 3dB point to the intersection point, we moved on a constant resistive circle clockwise. So here we're adding series inductor, and we can find its value by subtracting the Zi minus Za. And from moving from the intersection point to the origin, we moved on a constant conductive circle, also clockwise. So here we're adding a parallel capacitor, and we find its value by subtracting the admittance of the origin minus the admittance of the intersection point, as here in the solution. This is the Za value, the Zi and the Yi, and Z0 Y0. So moving from a point Za to Zi on constant resistive circle clockwise, we add a series inductor. Zi minus Za equals J.17, which equals J omega L. So from this equation we can find the value of L, the inductor. And after that, moving from the point Zi to the origin on constant conductive circle, also clockwise, we added a parallel capacitor. And from this equation, Y0 minus Yi equals J 0.23, and 1 over this value, 1 over J 0.23 equals minus J over 0.23, which equals minus J over omega C. So this is the second equation that from it we can find the value of the capacitor. Okay, to find the load impedance for the maximum power gain, we start from the 1.3 dB point. First we read its value. So this is the real axis. Za equals 3.1 plus J 1.19, and the admittance value is this is the 0.33 and minus J 0.17. So to move from this point to the origin, where we move on a constant resistive or conductive circle to reach the origin. So first I'm going to mark the origin circle using the pen. This is the constant resistive circle for the origin, and this is the 3 dB point, moving on a constant conductive circle. We reach this point, so this is the intersection point. I'm going to mark it to read its value. So Zi equals 1 minus J 1.5. Okay, and the admittance value is this is the 0.33 plus J 0.48, and of course the origin values Z0 equals 1 and Y0 equals 1. moving from this point on the constant conductive circle clockwise, so we're adding a parallel capacitor. And from the intersection point to the origin, we're moving on a constant resistive circle, also clockwise, so we are adding a series inductor. Now, to find the values of the inductor and the capacitor that we added, we first, since we moved from the YA to the Y intersection, we subtract YI minus YA, and this equals J.65. Then 1 over YI minus YA equals minus J over 0.65, and this will equal minus J over omega C. From this equation we can find the value of the capacitor. And then after that we moved from the intersection point to the origin, so we subtract Z0 minus ZI. So Z0 minus ZI equals J 1.5, and this value will equal plus J omega L, and from this equation we can find the value of the inductor. Thank you for watching.